Let us now turn our head towards one of the most beautiful topics of binomial theorem, namely binomial coefficients. Consider the expression, the expansion 1 plus x whole to the power of n. It is nc0 plus nc1 into x plus nc2 into x square plus nc3 into x cube ncr into x power r and so on ncn into x to the power of n. What is special in it? Nothing special. Instead of two variables, we have only one variable x, and in the first place we have only one. As a result of that, a very good convenience can be enjoyed here by observing the terms here. If you want to have the coefficient of x square, it is nc2, coefficient of x cube nc3, coefficient of x power 4 nc4, and the coefficient of x power r ncr. You need not run for any value of small r is equal to np minus k by p plus q like that. It is straight and simple. You can read the question, you can read the coefficients as you like. Coefficient of x power r is ncr. You see, hereafter these binomial coefficients nc0, nc1, nc2, etc., ncn are redesigned. Rather, the style will be revamped to denote like this: c0, c1 into x, c2 into x square, c3 into x cube, and so on, cr into x power r plus etc., cn into x to the power of n. By writing this big C, we are omitting to write n. Even though we omit to write n, it is itself understood that C3 means NC3, C2 is NC2, C1 is NC1, C0 is NC0, CR is NCR, Cn is NCn. Just for the sake of brevity only, to enjoy the briefness, we introduce this style of representing the binomial coefficients, and as we could already know, these coefficients C0, C1, C2, C3 and so on etc., Cn are termed as binomial coefficients. And of course, of special interest is the case for us to deal with the properties of these binomial coefficients. There are so many properties, so many useful and beautiful famous properties. One by one, let us study those properties well. So, in this discussion, what we could learn hereafter, nc0, nc1, nc2, nc3 and etc., ncn are termed or rather symbolized with c0, c1, c2, c3 etc., cn. Okay. Well, with this new notation, let us write 1 plus x whole to the power of n is equal to c0 plus c1x plus c2x square plus c3x cube plus cr x power r plus and so on cn x to the power of n. Let me call this f of x. Let me call this f of x. Good. What is f of 1? You please calculate. F of 1 is c0 plus c1 plus c2 plus c3 etc. etc. cn. And if you place 1 in the place of x, you will be having 1 plus 1 is 2 power n. Good. What happens to the fate of f of minus 1? You please observe. What is f of minus 1? 1 minus 1 is 0 of course, and here it is c0 minus c1 plus c2 minus c3 plus c4 etc. minus 1 whole power n into cn is 1 minus 1? 0, 0 power n. Good. From this, if you add these two, what happens? F of 1 plus f of minus 1 is c1 and c1 will be cancelled, c3 and c3 will be cancelled, c5 and c5 will be cancelled, and as a result you will be having c0 plus c0, 2 into c0, 2 into c2, 2 into C4 and so on etc. is nothing but 2 power n. Okay, if you add f of 1 plus f of minus 1, you are able to have 2 into C naught plus etc. etc. Well, you let me divide throughout by 2. F of 1 plus f of minus 1 by 2. What is that? C naught plus C2 plus C4 plus so on etc. 2 power n by 2 is 2 power n minus 1. Absolutely in the similar fashion, if you can subtract that by 2, what happens? While subtracting, C naught, C2, C4, C6 etc. such terms will be cancelled, leaving you 2C1, 2C3, 2C5 and so on. You please observe, we are framing f of 1 minus f of minus 1 by 2, so that you have C1 plus C3 plus C5 and so on is equal to 2 power n minus 1. Well, my dear, from this discussion we have 3 important formulae. What are they? Number 1, C naught plus C1 plus C2 plus C3 and so on. Cn is equal to 2 power n. That is the sum of all binomial coefficients is 2 power n, and sum of all coefficients of even powers of x. Coefficient of x square, coefficient of x power 4, coefficient of x power 0, coefficient of x power 6 and so on. What can you call this? Sum of the coefficients of even powers of x is 2 power n minus 1. This is sum of the coefficients of odd powers of x. You can easily grasp that. Coefficient of x cube, coefficient of x power 5 and so on, isn't it? So that this is a sum of all coefficients of odd powers of x. Not only that, hereafter we habituate to call these even coefficients and these odd coefficients, isn't it? Moreover, another important concept here, if at all there is any expansion, and if you can call it f of x, sum of all the coefficients is f of 1. Sum of all even coefficients is f of 1 plus f of minus 1 by 2. Sum of all odd coefficients is f of 1 minus f of minus 1 by 2. Like that, very useful conclusions could be drawn from this discussion. Well, let us now have those conclusions in an order. You please follow them. Expansion f of x, sum of all the coefficients is equal to f of 1. Sum of all the coefficients of even powers of x is equal to f of 1 plus f of minus 1 by 2. Sum of all the coefficients of odd powers of x f of 1 minus f of minus 1 by 2. And these 3 concepts are valid for any type of expansion in which there is only one variable, say x. Let us have an example. If 1 plus 2x plus 3x square whole to the power of n is equal to a naught plus a1x plus a2x square plus etc. 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 a2n x power 2n, then what is the sum of all coefficients? You consider this to be some f of x as per our habit. Sum of all the coefficients is f of 1. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 whole to the power of n is equal to 6 to the power of n. Then a naught plus a2 plus a4 plus etc. What will it be? It is f of 1 plus f of minus 1 by 2. What is f of 1? 6 to the power of n. What is f of minus 1? 1 minus 2 plus 3. 3 plus 1 is 4, 4 minus 2 is 2. 2 power n. 2 power n by 2. That's it. If C0, C1, C2, etc., Cn are the coefficients in the expansion one plus x whole to the power of n, then C1, C0 plus C1 plus C2 plus C3 etc. etc. Cn is equal to how much? 2n, 2 power n, the first one. Second one, C0 plus C2 plus C4 plus C6 and so on is equal to 2 power n minus 1. C1 plus C3 plus C5 plus C7, sum of all odd coefficients is also 2 power n minus 1. Now you subtract this minus this. What happens? C0 minus C1 plus C2 minus C3 plus C4 minus C5 and so on is equal to, what happens? This is 0. This can again be represented as sigma Cn, sum of all the coefficients. This can again be represented as sigma C2r. This can of course be sigma C2r minus 1. This can be sigma minus 1 whole power n into Cn is again 0 or even whole power n minus 1. Both are correct, of course. These are the fundamental properties. Beyond these, there are so many other. Let us now look at those properties. Look here. We know that 1 plus x whole to the power of n is equal to C0 C1x plus C2x square plus C3x cube x power n. Differentiate with respect to x on both the sides. What happens? N into 1 plus x whole to the power of n minus 1 is equal to 0 plus C1 plus C2 into 2x plus C3 into 3x square and so on etc. Cn into n into x power n minus 1. Right? Call this equation 1. If you take x is equal to 1, what happens? N into 2 power n minus 1 is equal to C1 plus 2 into C2 plus 3 into C3 plus 4 into C4 plus n into Cn is equal to n into 2 power n minus 1. Of course, this can be represented as sigma n into Cn. Of course, in the previous C0 into 0 into C0 can also be taken, therefore the sigma notation is meaningful. Again, if you take x is equal to minus 1 here, what happens? 1 minus 1? 0. 0 is equal to C1 minus 2 into C2 plus 3 into C3 minus etc. 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 So that this can be taken as minus 1 whole power n into Cn is equal to 0. These are the beautiful results. So that you are supposed to get them remembered as and when it is required. What is sigma n into Cn? It's nothing but n into 2 power n minus 1. What is sigma minus 1 whole power n minus 1 into n into Cn? Is again 0. Is again 0. Therefore, we could have observed that sigma n into Cn is nothing but n into 2 power n minus 1, of course, by differentiating this. Now, let us differentiate this once again with respect to x. What is going to happen? N into 1 plus x whole to the power of n minus 2 n minus 1 into is equal to 0 plus C2 into 2 plus C3 into 6x plus and so on, etc. Cn into n minus 1 into x power n minus 2. Okay, if you take x is equal to 1 here, what is going to happen? Come on. N into n minus 1 into 2 power n minus 2 is equal to 2 into C2 plus 6 into C3 plus etc. etc. n into n minus 1 into Cn. Therefore, this is the next result we have. And the RHS can be represented as R into R minus 1 into CR. R is equal to 0 to n. If you put R is equal to 0, 0 into 0 minus 1, 0 into anything is 0. There will be no such term. If R is 1, 1 minus 1 is 0 into C1. There is no term with C1. If R is 2, this is the first term, like that. Hence, this can again be taken as n into n minus 1 into 2 power n minus 2. This is the next beautiful answer. Well, basing on this one, we are able to derive so many results connecting C0, C1, C2, C3, etc. By taking x is equal to 1, by taking x is equal to minus 1, sum of all the coefficients, sum of all even coefficients, sum of all odd coefficients, sigma n into Cn previously, and sigma r into r minus 1 into Cr. Now at this juncture we are able to have. Let us have one more such thing. Again, let us start with the same expansion, that is 1 plus x whole to the power of n is equal to C0 plus C1x plus C2x square plus C3x cube and so on up to Cnx power n. Let us now integrate it with respect to x on both sides. What do you have? 1 plus x whole to the power of n plus 1 by n plus 1 is therefore equal to C0x plus C1x square by 2 plus C2x cube by 3 plus C3x power 4 by 4 plus etc. and so on x power n plus 1 by n plus 1. Good. This is again a beautiful expansion. 1 plus x whole to the power of n plus 1 by n plus 1 is therefore equal to C0x plus C1x square by 2 plus C2x cube by 3 and so on plus Cn into x power n plus 1 by n plus 1. This can again be taken as sigma Cr into x to the power of r plus 1 can be taken like this. Good. Rather than this, another beautiful result that can be obtained from this, if you can put x is equal to 1 in this expansion, in this step, what do you have? C0 plus C1 by 2 plus C2 by 3 plus C3 by 4 and so on, Cn by n plus 1 is equal to, you take x is equal to 1, what do you have? 2 power n plus 1 by n plus 1 by n plus 1. Another beautiful result. Okay. Well, the process is not over. There are still so many results that can be obtained by making use of this 1 plus x whole to the power of n. Let us now look at one more such important results. You please observe this: C0 CR, C1 CR plus 1, C2 CR plus 2 and so on. Cn minus r Cn is equal to 2n Cn minus r is equal to 2n Cn plus r. Very, 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 very useful, very, 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 very important also. It's a beautiful result. C naught into CR plus C1 into CR plus 1 plus C2 into CR plus 2 and so on, etc. Cn minus R into Cn is equal to 2n Cn minus R or 2n Cn plus R. Well, my dear, let us first observe its utility. Later on we shall think of its proof. Of course, the proof is also very simple, a single line proof. We shall definitely do that. Before going to prove this, let us enjoy its fruits. Suppose if you take R is equal to 0 in this, what is going to happen? Come on. C naught into C naught. C naught square plus C1 square plus C2 square plus and so on. Cn square is equal to 2n Cn. Either here or here, if you take R is equal to 0, either this gives you 2n Cn and this also gives you 2n Cn. Both of them are again equal to 2n factorial by n factorial into 2n minus n factorial, that is n factorial whole square. This is the most famous popular result that we have at our disposal. What is that? C naught square plus C1 square plus C2 square plus etc. Cn square is therefore equal to 2n Cn, or equivalently to say 2n factorial by n factorial whole square. Yes, this is nothing but in sigma notation can be called like this: sigma CR square. Sum of the squares of all the binomial coefficients is again 2n Cn. That is nothing but 2n factorial by n factorial whole square. How beautiful it is. Not only that, one more result is also there. What is that? See, we could have brought this into our observation by taking R is equal to 0. Now, my dear friend, you take R is equal to 1, what is going to happen? You observe. C naught C1, C1 C2, C2 C3, C3 C4 and so on, Cn minus 1 Cn. What is it? Sum of the products of binomial coefficients taken two successive coefficients at a time. C0, C1. You observe them? Successive coefficients. C1, C2, C2, C3, C3, C4, Cn minus 1 Cn is therefore equal to 2n Cn minus 1. Or equivalently, you can have it to be some 2n Cn plus 1 also. Yes, by taking R is equal to 1. Well done. Like that, you can obtain as many results as you can. If you take R is equal to 2, C naught C2 plus C1 C3 plus C2 C4 and so on, etc. is equal to 2n Cn minus 2. And if you take R is equal to 3, one more result, C naught C3 plus C1 C4 plus C2 C5 and so on equal to 2n Cn minus 3. Like that, you can have as many results as you can from that. That is why this useful result is so important. It's very important. And the way in which it is brought is also very clear. Let us spare just 1 minute to observe its proof. As it is giving us so many useful results, it is our moral responsibility to know the way in which it has been obtained. So let us spare 1 or at most 2 minutes to get its proof. We have 1 plus x whole to the power of n is equal to C naught plus C1x plus C2x square plus and so on, etc. CR x to the power of r plus etc. Cn x to the power of n. And just like that, x plus 1 whole to the power of n is therefore C naught x power n plus C1 x power n minus 1 plus C2 x power n minus 2 and so on, CR x power n minus r plus and so on, Cn. Now you multiply these two expansions, RHS of 1 into RHS of 2. What happens? C naught plus C1x plus C2x square plus etc. etc. CR x power r plus etc. etc. Cn x power n into C naught x to the power of n plus C1 x to the power of n minus 1 plus etc 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 plus CR into x power n minus r plus etc etc Cn into x to the power of n is equal to 1 plus x whole to the power of n into x plus 1 whole to the power of n, correct? And you could find no difference at all between 1 plus x and x plus 1. Hence, this expansion could again be taken as 1 plus x whole to the power of 2n, isn't it? 1 plus x whole power n into 1 plus x whole power n, that is 1 plus x whole power n plus n, that is 1 plus x whole to the power of 2n. Good. What do you want to have? We want to have the proof for the previous result, that is C naught CR plus C1 CR plus 1 plus C2 plus CR into CR plus 2. How can they be obtained? C naught CR. What is the coefficient of it? X power n minus r. Now you compare the coefficients of x power n minus r. What is the coefficient in the left hand side? C naught CR plus C1 CR plus 1 and so on. What is in the right hand side? 2n Cn minus r. That's it. Single line proof. That's it. Of course, the last term will be Cn minus r Cn is equal to 2n Cn minus r. It can also be taken as 2n Cn plus r. Why? Because we know that NCR is equal to NCN minus R. So 2NCN minus R is nothing but 2NCN plus R. Yes, like that we get it. Okay. One more thing. C naught square minus C1 square plus C2 square minus C3 square plus C4 square, etc., etc., etc. Of course, it is our moral responsibility to go through all the binomial coefficients. Not only that, it is our necessity, of course, to know all of them. This is C naught square minus C1 square plus C2 square and so on. So with alternate plus and minus symbols, this will be 0 if n is odd, and it is minus 1 whole power n by 2 into NCn by 2 if n is even. How can it be obtained? Look at this. 1 plus x whole to the power of n and 1 minus x 1 by x whole to the power of n. Consider the product and compare the coefficients of x power n on both the sides. C naught square minus C1 square, etc. Now compare the constant terms on both the sides. You have that result. So that's it about it. As it is time taking and it is just enough for us to go through the answer only. I'm not interested to go through the tackle with the proof of this. So you just keep that in your mind. Yes. Next one. A into C naught plus A plus D into C1 plus A plus 2D into C2, etc., etc., etc. A plus ND into Cn. That is a new sum, rather expression connecting the binomial coefficients. Well, my dear, you please observe all the coefficients which lie behind the binomial coefficients A plus D, A plus 2D and so on, etc., A plus ND. They are in AP. They are in AP, isn't it? We are now ready to obtain this sum. Of course, it's very simple. Let me call this sum S. The same S can be written from the last to first. How can it become? A plus ND into Cn, A plus n minus 1 into D into Cn minus 1, and so on, etc. The last term will be A into C naught. You add all of them. 2S is equal to A plus ND plus A, 2A plus ND into C naught and Cn, they are equal. 2A plus ND into C1 and so on, 2a plus nd into Cn. This is nothing but 2a plus nd into C0 plus C1 plus C2 plus etc. Cn. And we know that expression which is inside the brackets is nothing but 2 power n, 2a plus nd into 2 power n. This is 2s. So what is s? S is equal to 2a plus nd into 2 power n minus 1, isn't it? That's it. You look at that, how simple it is. And in order to use this result, you must be able to observe that all the coefficients which lie beside the binomial coefficients form an AP. Then the answer will be 2a plus nd into 2 power n minus 1. Yes, you could have seen. Yes. Let us observe one illustration for this standard result. C0 plus 3 into C1 plus 5 into C2 plus 7 into C3 and so on, n plus 1 terms. Is equal to C0 plus 4 into C1 plus 7 into C2 plus 11 into C3 plus etc. up to n term, n plus 1 terms. 2 into C0 plus 5 into C1 plus 8 into C2 plus 11 into C3 plus and so on. How can you get this? This is 2a plus nd. What is a here? 1. 2a means 2 plus nd. Difference is 1, 3, 5, 7. Difference is 2 into 2 power n minus 1. This is nothing but n plus 1 into 2 power n. What do you say about the answer for this question? A is 1, 2a means 2 plus d. What is the difference? 1, 4, 7, 11, etc. Difference is 3, but we want to have nd, that is 3n, 2 plus 3n into 2 power n minus 1. What do you say about this answer? Come on, guess that. 2a, that is 4, plus what is the difference? 3. 3n into 2 power n minus 1. That's it. About the utility of this result, famous result. Okay. Let us now turn our head towards one more new result regarding the binomial coefficients. For a little while, let us observe what is 1 plus I. Of course, it is a famous complex number, and if you can transform this 1 plus I into mod amplitude form, this can take the form root 2 into cos pi by 4 plus I sin pi by 4. It is very easy, of course, to observe it. What is cos pi by 4? 1 by root 2. What is sin pi by 4? 1 by root 2. If you can pull 1 by root 2 out, it will be again 1 plus I. Good. What is 1 plus I whole to the power of n? This is root 2 into cos pi by 4 plus I sin pi by 4 whole to the power of n. Well done. What is 1 plus I whole to the power of n? You try to expand that using binomial theorem. Come on, what can it be? C0 plus C1 into I plus C2 into I square plus C3 into I cube plus C4 into I power 4 and so on and so on. Cn into I to the power of n is equal to root 2 power n into cis n pi by 4. And this LHS can be taken as C0 I square minus C2 C4 plus C4 I power 5, I power 6 is minus C6 and so on. This is the real part plus I into imaginary part. C1 I cube is minus C3 I power 5 plus C power 5 minus C7 and so on is equal to root 2 whole power n into cos n pi by 4 plus I sin n pi by 4. My dear friends, I think you could have recollected the reason for this expression. We could have made use of famous de Moivre's theorem in complex numbers. Good. Compare the real and imaginary parts here. What do you have? C0 minus C2 plus C4 minus C6 and so on is equal to root 2 power n into cos of n pi by 4 and C1 minus C3 plus C5 minus C7 and so on is equal to root 2 power sine of n pi by 4. These are the beautiful result. Likewise, you can create as many results as you want and as you can. Of course, by changing this expression. Changing that expression, you can have as many as you can. Yes, this is one of the famous results. Regarding this binomial coefficients, there are some more expansions which are usually coming into our way of solving some numerical problems. Let us have one such expression, rather expansion. If 1 plus x square whole to the power of n is equal to a0 plus a1x plus a2x square plus etc. a2n x to the power of 2n, then what is a0 plus a1 plus a2 plus etc. a2n? Let us recollect the idea, or rather format, or rather habit of obtaining such sum of coefficients. If you consider this to be some f of x, sum of all the coefficients is suppose f of 1, isn't it? F of 1, let me name it to be some f of x. What is f of 1? 1 plus 1 plus 1, 3 power n. Suppose it is required to have a0 plus a2 plus a4 plus etc. etc. Then it is f of 1 plus f of minus 1 by 2. What is it? F of 1 is 3 to the power of n. F of minus 1 is 1 minus 1 is 0, minus 1 whole square is 1, 1 power n is 1, 3 power n plus 1 by 2. And of course, a1 plus a3 plus a5 and so on. This is equal to f of 1 minus f of minus 1 by 2 according to our previous assumption. No, not an assumption. The previous declaration, yes, it is 3 power n minus 1 by 2. Like that we have the expansions. Well, next one. The trinomial and multinomial theorems. What are they? If you have a plus b whole to the power of n, the formula which gives that expansion is of course called binomial theorem, and if a plus b plus c whole to the power of n is given, then it is of course called trinomial theorem. In this expansion, the number of terms is given to be n plus 1 into n plus 2 by 2. That is a beautiful question which is generally asked regarding a trinomial. And if there are some n terms like x1 plus x2 plus x3 etc. etc. xn whole to the xr, rather xk whole to the power of n, it is a multinomial theorem. It is called, the statement which gives the answer for this expansion is a multinomial theorem, and it is very simple of course. X1 plus x2 plus x3 plus etc. xk whole to the power of n is equal to sigma n factorial by r1 factorial into r2 factorial into r3 factorial into rk factorial x power r1 into x power r2 into etc. etc. x power rk r1 plus r2 plus etc. etc. rk is equal to n. This is the way in which we expand this multinomial expansion. A plus b whole power n is binomial expansion, a plus b plus c whole power n is trinomial expansion, and this is of course multinomial expansion. and we shall see, of course, as and when it is required and we need, if the need of the question demands, then we shall think of it. This is about multinomial theorem.